should have combed my hair in the rain once I come up on screen.
I didn't get too much rain. I was next door, so I had a very short walk.
Yeah.
So I didn't get too much rain on me.
Yeah.
Stand by 30 seconds, please.
Yeah.
Okay.
Welcome to the final CERIAS seminar for spring semester of 2016. Today we have with us Christopher Gutierrez, who is a Ph.D. student in the Department of Computer Science and CERIAS here at Purdue University. Christopher comes to us from Cal State, where he did his undergraduate, his bachelor's and master's work. Has been out here since, I believe, 2011. And is going to be talking to us today about the work that won the Best Poster Award at the CERIAS Symposium held last week. So with that, I will turn it over to Chris.
Thanks. So today I'm going to be presenting ErsatzPasswords, ending password cracking and detecting leakage. So this work was pioneered by Mohammed Al-Masheka, which he graduated last year. And this is some of the work I continued on from that. This is also work with Spaff and Mike Atala and Jeff Avery. So the paper in which some of the stuff here is detailed was presented in ACSAC 2015. There's a journal submission underway with some of the new results that I'll talk about towards the end of the presentation. So this work, we're looking at passwords and protecting them. They're a big problem. Here are some news articles. It seems like these things are reoccurring. Evernote, some password leakages there. Yahoo, eHarmony, LinkedIn. I'm sure if you go out and Google right now and search for some stuff, you could see some more later leakages. Passwords are kind of here to stay, and we need to figure out a better way to protect them. So in this work, we're going to be using deception to try to help mitigate some of the leakages. So here's kind of the general threat model, right? You have a user that's using some online services like, some social network or what have you. They communicate their password, and somewhere out on the net, the password is stored, say, with some cryptographic hash with some salt. The problem is if there's an insider that has access to that web server, or there's the web server the server gets compromised, then someone can steal those passwords and run a brute force attack, breaking some of the weak passwords. So with the ErsatzPassword, our goal here is to eliminate the possibility of offline dictionary attacks by injecting some deceit into the way we store the passwords. Also, since we're injecting deceit, we're giving them false information. If they go out and try to crack these passwords, rather than producing a real password, they produce a fake password. If they go out and try to log in posing as the user, an alarm is triggered. And you can react appropriately. So notifying the user, system administrators, locking the account, or etc. So here's the kind of a high-level view of what ErsatzPassword, what our system actually does. It uses, in the center here, we have the hardware security module, which is critical to our to the way we generate these password hashes. So on the left-hand side, you have your master.passwords file, say stored on like a BSD system with several user accounts. So I'm going to guide you through kind of the process of what ErsatzPassword does. First, when a user types in their password, say for the first time they log in to create a new password, a fake password is generated. And I'll talk about how that generation actually works. But say we just come up with some simple password as kind of like the decoy password. Next, we'll use the hardware security module to generate a new password salt and hash And these salt and hashes are indistinguishable from what you would expect to be stored on a real system. And then we write out these new modified hashes out into the password, the file that stores all the password hashes. And I'll dive into the details of the generation and how that all works. So we have two threats to consider here. We have an offline adversary. So this is an adversary that obtains the username and password hashes, but doesn't have access to the actual machine in which the passwords are stored. Think of this as someone compromising a machine, stealing the hashes, running it through John the Ripper, and posting all those passwords and usernames out in like Pastebin or some other website. So the attacker is able to download that information and perhaps use it to go log into those accounts. So we assume that the attacker may be aware that the ErsatzPassword is actually in place on the server which these hashes were generated, but does not have access to the server to actually query the hardware-dependent function, which we use in our experiments, an HSM, hardware security module. On the other hand, we have an online adversary. So this is the adversary that actually has access to the machine, which generates the passwords and hashes that are stored on the actual server. So this is basically the same threat model, but they have access to the actual machine which the password hashes are generated. Notice here, though, if the adversary is able to subvert this hardware security module, the security basically reduces down to what we had to just a conventional hashing scheme. Just to say here that our scheme that we're proposing is a supplement, not a replacement to your traditional mechanisms to safely store passwords. This is just another layer of security that we're providing. So here I'll talk a little bit about the technical details. So I'm going to guide you through how the system would work if you're a brand new user. Actually, no, sorry. This is if you have an existing user with some hashes stored on the server in your traditional way. So up at the top we have UI, which is the user. A is the cryptographic hash of the password, and S is the random salt. We first push this the password hash through the hardware-dependent function, which we then push it through your hashing scheme that you have on your server, appended to the salt. So that's the third step here on the bottom, to produce beta. Beta is your new hash that you saved on the on your server. So this first step that we just went through is just kind of the initialization to produce these new hashes stored on your server. At some later point when the user logs in, now that we've initialized the system, they provide their username and password, so UI, the username, PI, the password. We use the password to generate this ErsatzPassword, this PI star. I'll talk a little bit about the details of how you generate that. Just for now, it's just some other, our deceptive component, it's some randomly generated password that will pose as the fake password. So once we do that, we generate this ErsatzPassword, we generate this new salt, and this is really kind of the critical component of the scheme. We use the true password appended with the username, and we XOR that with the ErsatzPassword that we generated. And this is going to be our new salt that we're storing on the server. One note, keep in mind the identity here. So the actual ErsatzPassword is equal to this hardware-dependent function that we pass through the username and password XORed with the salt. And that'll hopefully be clear here in a minute why that's an important step. Once we do that, we produce this new hash now that the user has provided their true password, and we store the new salt and the new hash in our database. So this is at the very bottom. We have beta and S. Beta I being the hash for the user I and the salt for user I. So now, we want to see how this works. Now a user is going to log in. They provide their username and password, and we're going to run through kind of what happens in the Ersatz scheme. So first we check to see if the user provided the correct password. So this is the identity that I mentioned earlier, that if the user provided the true password, the HDF appended with the true password and the username XORed with the stored salt, it will produce a BI. And notice here on the bottom I have a note. The reason, if the user provided the true password, this calculation should come out to be the ErsatzPassword. If the user enters in so part of our scheme, we first check to see if they entered in the true password. Next, we check to see if that failed, that first step failed, we check to see if the ErsatzPassword was provided. So if the ErsatzPassword was provided, we generate an alert. Else, if both of those steps fail, then we just tell the user that their authentication failed. Any questions?
So
this is kind of the tricky part of the talk,
Yeah.
so we can.
if you can explain, so what's happening in the second step? What exactly has happened there?
So the first step, we check to see if the user provided the true password, and we run it through our hardware dependent function. The second step, if the user provided the ErsatzPassword, so let's see if I have my mouse here. Where did my mouse go? So I'll just try to explain it. So if the user provides PI, which I highlighted in blue, if this PI is the same PI star that we produced when we generated the hash, then we trigger an alarm, and it's because of this identity down here in the bottom. If you look closely, what's that? Yeah, I'll walk around. So notice here so just ignore this. Right here where we produce the salt, this is the salt we produce, which is, typically in your traditional system, it's just some randomly generated number, right? So here, the way we produce it is we run it through our hard dependent function with the true password XORed with the ErsatzPassword. And so up here, when we check this, if the user provided the true password, this SI cancels out with what we had before, right? If you look here, just replace this part up here with the SI. These two portions cancel out, and we're left with the ErsatzPassword. So we first check the true password, and if the true password is equals our BI that we have stored, then we authenticate the user. Next, we check to see if the PI that the user provided is the ErsatzPassword. And we do this by just running it through the hash without pushing it through the hardware-dependent function. And that will produce, if they're equal, then we trigger an alarm.
So my question is, why is that an alarm? Why is that something that should trigger an alarm?
Right. So the idea here is if an attacker steals all these passwords, which is our beta, since they don't have access to the HDF, they don't have that physical access, we're assuming they don't have access to the hardware security module, then when they run a brute force attack with a dictionary, they're only able to push through dictionary words and not actually calculate that HDF portion. So it triggers an alarm because if the attacker went through a dictionary for PI, then at some point, if the password's weak, then it's going to produce the beta I that can be produced without the HDF. Any other questions? All right, so 3 main properties. Like I mentioned, checking the password requires physical access to this hardware-dependent function. In our scheme, which I'll talk about some of the implementation details here in a minute, we use the hardware security module, which is just something that you can purchase online. Since the attacker doesn't have access to the hardware security module, they can't do an offline dictionary attack. If they steal these passwords and push it through John the Ripper, it will produce it will make it look like they found the true password, but in fact it's not the true password. So cracking returns ErsatzPassword for every account. So rather than some of the other work of putting some false information in password databases, you could put like a fake user and password, and maybe have something at the authentication server checking to see if the fake user and password was provided. Our scheme rather produces a fake password for every user account that's stored in our system. And what's really nice is that we maintain the same password format, so that if an attacker were to just look through the password file, it wouldn't show anything different. They, of course, can run some other statistical analysis to try to detect this if the scheme is in place. But the goal here is to deceive the attacker into using these fake password files that are generated through a brute force attack. So I mentioned earlier this generation function, which is the way we produce these fake passwords. There's some properties that we want to meet for these fake passwords. We want them to be plausible, so that if an attacker were to crack these passwords, it looks like something that an actual user would have produced. Since we're using we can assume that we can use the true password to help generate some of these fake passwords. We want it to be non-deducible. So if an attacker were to look at a fake password, they should not be able to deduce the true user's passwords. Further, it should be typo resilient. So if if a true user types in their password and maybe mistypes it, the edit distance should be significantly far enough so that we don't generate false positives. The crackability of the passwords stored in our hash file should reflect reality. So if you have a certain percentage of users that you expect to have weak passwords, that should also be reflected in the way in our password file. Finally, the fake passwords that are produced should adhere to the same password policy that's out on your system. There's several, in the paper we list several ways of choosing this generation function. If you want details, they're in the paper. But the highlight here is just we want to follow these properties for generating the ErsatzPassword. Our scheme has a very simple method of producing a backup for since we're using a hardware security module, if somehow that is compromised or destroyed or stolen, the keys are lost. So we want a way to actually recover. And so this scheme, we're just using a public-private key. The private key is never used in operation. It's stored somewhere maybe in a vault. During the initialization, which I stepped through earlier, of converting all of these stored password hashes into these ErsatzPasswords, we basically make a copy and put it in the backup storage. And we do this by encrypting it with a public key, and then creating a log every time there's a change to the password file, and encrypted with a public key. If at some point the hardware module fails or something gets compromised, we can backtrack and recover that, and then use a new hardware security module, hard dependent function to reinitialize the scheme. So implementation details. We used a UBHSM. There's a picture of it on the right. I have an older version. It's much larger. This one's pretty inconspicuous. For the hardware dependent function, we're just using a HMAC with a SHA-1 with a key that's stored on the hardware security module. You could use a TPM or a PUF, physically unclonable function. So the implementation, we did 3 separate experiments, somewhat related. We first implemented the ErsatzPassword scheme on a PAM Unix module, which is the authentication module on Unix-like systems. We did this on a free BSD operating system. We also integrated the ErsatzPassword scheme on the lightweight directory access control protocol, LDAP for short, with a Linux client server model. And we also looked at the Pythia PRF service, which was a paper published in Usenix 2015. All the code is available on GitHub. And kind of the rationale for choosing these three authentication schemes. So we wanted to show and demonstrate the flexibility of the ErsatzPassword scheme. We're making a claim that it's not terribly complicated and that integrating these on its existing authentication systems is not too much work. So I'll talk about some of the performance details here. So this is for the PAM Unix module. For the setup, we used SHA 512 hashing. This is the H around all the HSM. Let me back up. I should have actually put a picture there. So this is the H that produces the hash at the very end on the beta step, the second to last step. Oops. For the ErsatzPassword generation function, we just randomly selected a 6-character dictionary word. I actually just went on, looked up the official Scrabble dictionary and found all the 6-character length words. This is, the idea here is to kind of produce something that's crackable. And we used a fixed password of 6 characters for our experiment. So we fixed all these parameters and ran it through 1,000 times and produce this latency plot. So it's actually there's quite a big overhead here. The baseline, which is the PAM Unix module without the ersatz mechanism, it's on average about 5.4 milliseconds. Our scheme is quite a bit more than that. It's about 280 milliseconds on average, and the distributions don't vary too much from detecting the true password versus detecting an ErsatzPassword. For the LDAP scheme, the setup was we wanted to just measure the latency caused by the ersatz mechanism. So our client user network was all done on a local area network. So a little overhead from networking latency, and we did no channel encryption. So we're just looking at specifically the ersatz latency. Again, it's about 2 to 3 times slower by using our scheme. It's a little bit better than what we had in the PAM Unix module. The median for the true and ErsatzPassword was about 0.9 seconds, 0.8 seconds, while the baseline was about 0.3. So the Pythia PRF Service, we looked at this paper, and we found it was a really interesting method that they propose where they use partially oblivious function to basically split up how the password is stored, and they produce a mechanism to rotate the keys in a very clever way. And we integrated our ersatz scheme into this, and what's nice is their scheme allows for quick rotation if something is compromised, and our ersatz scheme allows a mechanism to detect if something is compromised. So we downloaded their source and integrated their ersatz scheme into their system and produced these performance latencies. Again, quite a bit of an overhead, but it's really up to the use case if this latency is justified to increase a little bit of the security of the system. Some of the details about the code. There's really 2 libraries written, one in C and one in Python. The C library was used for the PAM Unix experiment and the LDAP experiment. About 250 lines of code. For the Pythia PRF service, where the Python library was about 100 lines of code. The difference between, and so this library kind of produces all the core functionality for the Ersatz password scheme, and the figure below just details some of the integration that needed, some of the code that needed to be changed to integrate into these systems. Between 30 lines of code to 60 lines of code, depending on the scheme that we're integrating in. In the paper, we talk a little bit of the details how this could be used on a TPM rather than an HSM. It's basically the same steps: initializing the TPM, storing creating some key to be for the HMAC to use, creating a handle to the key, and just using that handle anytime we want to produce a hash and verifying authenticating a user. One of the weaknesses here is, though, similar to the HSM scheme, if the TPM password is compromised, then they can an attacker could potentially wipe all the keys on the TPM. So that's about it. Any questions?
You explained it well, but I just want to say it back to make sure I got it.
Okay.
So you're generating ErsatzPasswords randomly across users, all right? And then when someone logs in with a hacked password that's not an ersatz substitution where there should be one, it detects that, and then it triggers an alarm that's saying, hey, someone is not here that should, someone's here that shouldn't be. And then usually what happens with that alarm? Who sees it? How's it reacted to?
Yeah, so the policy around the Ersatz scheme, we kind of left it up to the practitioner. Right now, the actual implementation just generates a panic, just a message that comes up. But if you download the code and you want to actually run this stuff on a real system, you could just basically change out the panic message to whatever you want it to do. Notify a system administrator, lock the account, whatever policy you really want.
So the YubiKey is sitting on a server?
That's right.
Okay.
Yeah, actually one of the future work that we want to look at, so in the LDAP scheme, we're requiring the user to touch the LDAP server every time they want to authenticate. In reality, the way this works is the first time you log in and you communicate with the LDAP server, they send basically a hash of the password. It depends on the details of the scheme because it's kind of up to how the system administrator wants to use it. But nonetheless, there's a caching mechanism that rather than having the user communicate with the LDAP server every single time, they store the credentials on the system locally, so you don't have to communicate with the LDAP server. There's a challenge there with producing these ErsatzPasswords. So we want to look at that in future work.
On the one, because see what you'd have to do, you'd have to produce the actual hash, which is exactly what you're trying to protect from being disclosed.
That's exactly right.
But at least it wouldn't be, it would be just the few users, just the cache. You wouldn't get the whole file. So you wouldn't be able to attack
That's exactly
more
right.
users.
It still reduces the attack space.
Yeah.
But if you were to, and in the paper we detail some mechanisms to kind of fall back on, right? If you just send them the hash of the real user password, we're back to where our security scheme was before we introduced ErsatzPassword. So it's no better or no worse than before. You could come up with something clever if you're able to do some attestation. Maybe there's a TPM on the say your laptop. It's a mobile device that doesn't have internet access all the time, to do some kind of communication, to do the Ersatz scheme locally on the cache. But some of those details need to be worked out.
I have another question.
Yeah.
Did you do any measurements of the, this extra time? Is that all in that hardware security module, or how much of it?
Yeah,
Are you able to measure the actual time spent there?
Yeah, we did. We it's detailed in the paper. I can talk about it. So the the programming interface that Ubico provided was written in Python. So we saw a huge latency overhead because we had at one point in our C code for the PAM Unix module, we had to stop everything, switch over to Python code, run the APIs, get the output, and then switch back. And that caused a lot of overhead when we ran through our analysis.
So that's why the Python was faster.
That's right. That's right. Which is counterintuitive, right? You would think the C code would be faster. And also, this device is communicating through USB. If there was a hardware implementation, maybe on the actual bus or like on the motherboard, it might be faster. One thing to note is we didn't code this up for to be the most optimal solution. There could be some speed up if you were to rewrite the APIs for in native C. Then I imagine it would be much faster. You wouldn't have that overhead of switching between C and Python.
Any other questions? Anything else you want to?
Thanks for listening.
Okay. Well, thank you. Appreciate your stepping in.